Greetings everybody, and now let's look at some examples of linear transformations. So the first one that we have is really just multiplication by a scalar. So if we've got any alpha that's in our scalar field, then we can define a linear transformation from a vector space to itself such that t just sends v over to alpha times v. Now to see that this really is just a linear transformation, if we apply t to v plus w, then that's just alpha times v plus w. Well, our vector space property, our vector space distributive property, just lets us distribute that to alpha times v plus alpha times w. Well, what are each one of those? Just t applied to v and t applied to w. So it does respect vector addition. To see that it respects scalar multiplication, if we do t times gamma of v, then that's just alpha times gamma of v. Well, again, our vector space properties, we can regroup those. It's like we're multiplying by our scalars. But in our scalar field, since it is a field, we've got the commutative property, so that we can just do gamma times alpha, and that's when our field is a commutative field. So we've just got gamma times alpha, and so again we just use our vector space property from there. We can pull that gamma out, and so that's gamma of t times v. And so when our base field is the real numbers or the complex numbers, then just multiplying by a scalar does give us a linear transformation. Okay. Now if we kind of restrict to the special case when our field of scalars is the real numbers, if alpha happens to be greater than 1, then it's called a dilation. If alpha is in between 0 and 1, then we have a contraction. In the case that alpha is negative, then we have a reflection in addition to having that dilation or contraction. If we look at two-dimensional space, then we can talk about reflections across the x and y axes. So the reflections across the y-axis, if we just take a point xy, then that gets reflected to the point negative xy. And so what happens, we get a linear transformation that's doing this, and we've got a vector multiplication. For that, really, we're just changing the x value, so we've got negative 1, 0, 0, 1 times our input vector xy. If we then do a reflection across the x-axis so that y just goes to negative y, then in matrix form that thing is going to look like 1, 0, 0, negative 1 times our vector xy. And so for finite dimensional vector spaces, what we usually do is write our linear transformations as matrices with respect to kind of the standard basis. So we've got our standard basis where E1 is just going to be a 1 in the first component, 0 everywhere else. E2 is 1 in the second component, 0 everywhere else, all the way out to E sub n, which is 0 everywhere except for the nth component. So in addition to dilations and contractions and reflections, we can talk about rotations. So a rotation is really just a linear transformation from R2 to R2 in this case. And if we want to kind of restrict, or if we want to just so that we keep things straight, say E1 and E2 is going to be our regular standard basis for our domain values, and then for our rotated reference frame, we'll say that one's going to be E1 hat and E2 hat. So we can ask ourselves exactly what is E1 in terms of E1 hat and E2 hat. Well, relative to our rotated reference frame, E1 hat and E2 hat, E1 appears to be rotated clockwise by that angle theta. And so just kind of using our regular trig to come up with what those magnitudes are, we can see that E1 is just going to be cosine of theta times E1 hat minus sine of theta times E2 hat. If we do the same thing for E2 in our new reference frame, so E2 is going to be out here somewhere, then we've really kind of with respect to our rotated reference frame E1 hat and E2 hat, or the X prime and Y prime directions, then E2 ends up looking like the sine of theta times E1 hat and the cosine of theta times E2 hat. So that if we've got a general vector v of the form v1, v2, and again this is with respect to our standard basis, ve1 plus v2, e2, then if we apply these rotation using our linear transformation property, well, that's v1 times r of e1, v2 times r of e2, and if we just replace each one of those vectors by cosine of theta e1 minus sine of theta e2 hat, and sine of theta e1 hat plus cosine of theta e2 hat, do some rearranging of that, group them together by e1 hat and e2 hat, then we end up with an expression in matrix form that looks like cosine of theta, sine of theta, minus sine of theta, cosine of theta times our vector v1, v2. And so we can talk about a clockwise rotation by an angle theta being given by this matrix cosine of theta, sine of theta, minus sine of theta, cosine of theta. Now, sometimes we actually write this as a function of theta. Sometimes we might write it as a subscript for theta if we just kind of want to be a little more general about that. And so likewise, if we wanted a counterclockwise rotation, then we can just replace theta by negative theta. And if we do that, use our odd and even properties, then we get a matrix representation that looks like this. Okay, now something to note, at least in this case, is that r of negative theta is going to be the transpose of r of theta. And likewise, r inverse of theta is going to be r sub negative theta, so a rotation in the with an angle of the negative value, and that's also going to be the transpose of theta. So these kinds of properties where the inverse ends up being the transpose, we'll see those guys coming up a little bit later, and so that's something to kind of make note of here. And so with this, we kind of gone through a real brief description of some of the types of linear transformations that we can deal with. And probably in the next video, we'll get in a little more in-depth into those reflections and see how we can write those in terms of the stuff that we've already done. So stay tuned for that, and I will see you guys next time.